Today we're going to be looking at Ohm's law. V equals IR. Essentially, on a graph, this would display that the voltage and the current is directly proportional, a straight line, a straight gradient. And this would be a constant, and that constant is the resistance of whatever component we're looking at. If we take an inverse of this, however, we would have a graph like this, comparing current and resistance directly. This would be what the graph looks like, just a steep curve, an inverse curve. And the entire area beneath this graph, that's going to be equivalent to voltage, the potential difference. Now, let's try some problems with current, voltage, and resistance. Our first problem that we have a cell in a circuit. We have a filament lamp, and we have an ammeter. The cell has a voltage of 6.0 volts, and the current is recorded to be 4.5 amps. You can pause the video and find the resistance. To find the resistance, simply divide the voltage by the current, and this will give us a value of 1.3 ohms, just two significant figures. Let's try another problem. For our second problem, we're going to be attempting another circuit. However, this time we do not know the EMF, we do not know the voltage from the cell, and we're using a thermistor this time. So here's our circuit. The resistance of the thermistor is recorded to be 2 kiloohms, and the current on the ammeter is recorded to be 6.9 microamps. Now, to find our voltage this time, we do have to multiply these two, but we have to consider their units as well. So here we have 2000 ohms, and we have to multiply by 6.9 times 10 to the minus 6, considering the micro unit is to the minus 6. Multiply these two values, and we should get an answer of 0.014 volts to two significant figures. Let's try another problem. This time, we're going to be looking at the equation for power. P equals VI. This is simply derived from the fact that power is just energy over time, and energy is equivalent to charge times voltage. We know that charge equals I times T, so upon simply rearranging for power, we can then say that power is simply I squared R if we substitute V equals IR in and rearrange V over I to get R. We can also say power is V squared over R. So these two equations are pretty critical, but you can use either one to figure out the power dissipated over an object or component in the system. Let's take a look at a question. In this question, we have a battery going around in a circuit, another filament lamp this time, connected to an ammeter, and the voltage is unknown. However, we do know the current going through the circuit. It was recorded to be 0.5 amps, and we know the resistance of the filament lamp, which was recorded to be 0.2 milliohms. You can pause the video to answer this question again. And now we're going to solve for it. The question is to find the power across the filament lamp. Using our equation, here we have the current and we have the resistance. We do not know the voltage, so that's not going to be part of our equation. Hence we'll use I squared R. Power is 0.2 times 10 to the minus 3 squared times by 0.5, and altogether that'll give us an answer of, bear with me for one moment, 2 times 10 to the minus 8 watts. Thank you for watching the video. Leave a like and a comment if you want, and see you next time. Goodbye.